Sound is a wave and exhibits wave-like behaviors, including the wave phenomena of wave interference. When two sound waves interact, they form constructive and destructive patterns, and the property of sound intensity can be used to locate the minima and the maxima. By generating different frequencies, we can find their respective wavelengths and determine the constant of the speed of sound. Speakers were placed at a distance 1 meter away from each other. The distance was measured using a string, whose length will be determined using the marble drop method. 1 meter away from the speakers, a piece of masking tape was placed. The green string was used to measure this distance experimentally. The center between the two speakers was marked. Frequencies of 1000 to 3500 Hz, increasing at 500 Hz were used, generated using the tone generator on 5-aux, connected to two identical speakers. A second phone running the audio amplitude detector on 5-aux was moved along the piece of tape. Starting from the center, when the phone reaches a minimum, the position of the phone on the tape was marked. 3 trials were taken per frequency. Each frequency had its own tape. A lap stand was set up so the tape was perpendicular to the table, and the marked center was touching the table. The marble drop method was used to find each distance. Due to human error in holding the marble, 3 trials with heights within the range of the marked data points of the tape were taken. This was repeated on 2 different surfaces to minimize the effects of the surface material on the inelastic collisions. The same method was used to measure half the length of the string.
The averages of all heights were taken. The uncertainty of the averages were calculated using half the range, since the first minima has a path difference of half a wavelength. The wavelength of each frequency was calculated using this equation. Lambda equals 2 times y times lowercase d divided by capital D. Since the double length of both strings were measured to be 1 meter, the wavelength was simply double the height of the marble drop.
The average wavelength was plotted against the frequency, and an inverse function was shown as expected. There was an obvious outlier at 2500 Hz. The graph was linearized to have the inverse of the distance versus frequency plotted. The slope is expected to represent the inverse of the speed of sound. The maximum and minimum slopes were used to calculate the error bars, and these are generated by manually graphing a linear line using Logger Pro. Our final experimental value for the speed of sound was 329 plus minus 14 meters per second. At 0 degrees, this would be 316 plus minus 17 meters per second. Compared to the literature value of 331, the percentage difference was 4.5%, and 331 is within the quoted value of 316 plus minus 17 meters per second. Therefore, our experimental value is valid. The biggest source of systematic error is the phone's function, because data collected through 5-aux may have varied depending on the phone's hardware. Another source of systematic error would be the estimation of the room temperature. This would have skewed the conversion to 0 degrees for the speed of sound. The biggest source of random error was determining the height using the marble drop method, because the initial drop height in itself had great uncertainties, and the marble may have been dropped with initial velocity due to human error. Another uncertainty would be the width of the speakers on the phone, and an improvement to this would be using a smaller speaker with a smaller diameter. Lastly, there was uncertainty in cutting the string and drawing on the tape, which would have contributed to the random error on the height values.
Standing waves form when two waves with a similar frequency superimpose upon each other. An easy way to achieve a standing wave is by reflecting an off surface back towards itself. In practice, in a pipe where one end is open-ended, a node will form at the closed end and an antinode will form at the open end. This gives the general relationship for the harmonics of the standing waves. L net equals to 1 plus 2n all over 4 times lambda. Contrary to what most textbooks say, the acoustic length of the standing wave does not equal the length of the tube from its open end to its closed end. The acoustic length of the sound wave extends slightly beyond the length of the tube. The relationship of the length that extends beyond the tube, delta L, is given. Delta L equals to 0.61 times r. To take this into account during data processing, we will measure the radius of the pipe with the equipment accessible to us. Now the wave equation is given as c equals to f times lambda. By relating these 3 expressions together, we can find the speed of sound if we find the acoustic length of the pipe, the harmonic number, the frequency of the sound entering the pipe, and the inner radius of the pipe. We decided to use a simple pendulum setup to measure the length of the glass tube and the radius of the glass tube. The length of the glass tube was measured using the pendulum by aligning the center of the pendulum bob, the marble, to the level of the water and raising the string to the top of the tube. To ensure that the string was perpendicular to the tube, 2 small markings were made on the tube beforehand using a straight wooden plank and the phone with an inclination setting. The radius was measured indirectly by first finding the circumference of the tube on the inside. This was done by wrapping up the pendulum string as such 9 times around the test tube with rolls of paper taped around it in such a way that it perfectly fits inside the inner tube. 9 loops were done to increase the overall length of the pendulum, and thus to increase the time of each period, such that the percent absolute error would be reduced. The period t of a simple pendulum can be expressed in terms of the effective length L and the local gravitational constant g, when the angular amplitude is small. Now the next thing we have to do is to measure the period of the pendulum. Using the acoustic stopwatch feature, we measured the time it took for the pendulum to oscillate 20 cycles to reduce the percent absolute error from human timing errors by tapping on the nearby table. The following tables of data were then generated. The absolute errors of our raw measurements are given as, so for the time taken for the pendulum to swing 20 cycles, we assigned it a value of plus minus 0.4 seconds. The human reaction speed varies between 0.15 to 0.25 seconds, so we assume that our absolute error for starting and ending the timer are both 0.2 seconds respectively, so adding them up you get 0.4 seconds. Lengths. The marble had a diameter of a bit over a centimeter, so an additional plus minus 0.3 centimeters of absolute error was added upon our length measurements from the pendulum equation due to the act of eyeballing the marble center of mass to the liquid level. Another additional absolute error of plus minus 0.2 centimeters was added to our length measurements for 9 times the diameter of the inner tube due to the way that we wrap the string around the test tube. Temperature. This is by far the greatest contributor to the percent absolute error of our experiment. We estimated that the temperature of the room was 20 plus minus 5 degrees Celsius. To find the local gravitational constant, we used a gravity anomaly map for Canada, as displayed. From the results of our experiment, we got an empirical speed of sound at 20 degrees Celsius to be 338 plus minus 8 meters per second. We then used this value to extrapolate the speed of sound at 0 degrees Celsius, and we found it to be 326 plus minus 10 meters per second.
In this experiment, we will be finding the speed of sound at 0 degrees Celsius by using Firefox Acoustic's watch and a clap method. As 2 phones are placed within a certain distance keeping them apart, and a sound is made close to one phone with the acoustic stopwatch, the watch close to the clap starts first, while the other one starts at a delay given by delta t is equal to d over speed of sound. Then, as the second clap is initiated, the sound stops the watch immediately, followed by the first one stopping after the same delay. The difference in the measurement of both watches is then twice the delay and can be represented by the basic kinematics equation v is equal to 2 times d over delta delay. The distance between the phones was then found using the pendulum method used in method 2. The independent variable in this lab is the distance between the phones, and the dependent variable is the time delay. The control variables in this lab are the elevation of the phones and the side of the mic each phone faces. 7 different distances were chosen with 3 trials per distance, giving a total of 21 trials. The distance coordinates of each point were then doubled and plotted against the time coordinates of those points. This graph then gave the slope with a value of equal to speed of sound at room temperature. The errors in this lab included the temperature fluctuations in the room, which will affect the speed of sound. The orientation of each clap and any potential barriers in the air also affected this result. The data was then interpolated to find the speed of sound at 0 degrees Celsius from the assumed 22 degrees plus or minus 4 degrees before, which was considered to be the room temperature here. This presented a percent error of 6.93% from the literature value of 331 meters per second, and a random error of 11.3%, showing a total systematic error of 4.37%. It showed that our value for speed of sound was 345 meters per second from the literature 331, and had a random error of 39 meters per plus or minus 39 meters per second.
The Doppler effect refers to the phenomena in sound waves where the change is observed in the frequency of a wave due to the movement of the observer and or that of the wave source. When the source of sound moves toward an observer, the wavelength compresses, forcing the perceived frequency to be shorter than the source frequency. Similarly, when an observer moves toward a source of sound, more wavelengths of sound are heard in a less amount of time, thus changing the frequency of sound. The speed of sound is how fast sound moves through the air when the sound source is stationary. When a speaker attached to a spring oscillates up and down with the observer directly below, the observer will perceive a constantly changing frequency as the velocity of the speaker is constantly changing. In this experiment, 3 devices running Firefox were used, where device A emitted a constant frequency of 1000 Hz using the tone generator. When checking what value to use for base frequency, another device using the audio autocorrelation app in Firefox was used to give a value of 999.79 Hz, which was recorded as the base frequency in the Doppler's effect sensor. Device B was attached to device A to record the absolute acceleration when they oscillated using the acceleration without gravity app within Firefox. Device C was placed at the bottom of the mechanism, which recorded the change in frequency using the Doppler's effect app in Firefox. Both device A and device B were connected to a mass which was connected to a spring. The mass was then pulled down and oscillated, where the change in both frequency and acceleration was recorded.
The greater the velocity of a moving source, the greater the difference the perceived frequency will have from the actual frequency. Therefore, these points of maximum and minimum perceived frequency correspond to when the source of the sound is at its maximum velocity. Using the Doppler's effect formula for a moving source and an observer at rest, after isolating for the speed of sound v, we get this formula. For the perceived frequency values in the formula, we choose to use the points of the maximum and minimum frequency in the frequency time graph. The maximum velocity of a moving source was calculated through the following formula, which was derived from equations for a simple harmonic motion system. Using the maximum and minimum on the crests and the troughs, the speed of sound was calculated for each value of acceleration and perceived frequency. These were then averaged to find the value of 343.4 meters per second. We then found the uncertainty value, which was found using half the range. This also shows the high uncertainty and variance in the experiment.
Since we assume the room temperature of 20 degrees Celsius, 0.60 times 20 equals a decrease in speed of 12 meters per second. Therefore, 343 minus 12 equals to 330 meters per second at 0 degrees Celsius. There were random errors on the change in frequency. This was because the mass had velocity on the x and z axes, as well as there being background noise, causing inaccurate results. There was also uncertainty on the base frequency since there was distance between the Doppler effect sensor when the phones were at rest. The temperature was also assumed to be 20 degrees Celsius since the initial temperature inside the room was unknown.